we want to talk about thermal energy. Thermal energy. This causes some people a problem. One of the issues here is we have three words in physics that are similar but each different. The word thermal energy, temperature, and heat. Do you know the difference between the three? Let's start with temperature. Temperature measured for now in degrees Celsius is an indicator of how much movement there is on an atomic scale. When we have a mercury thermometer, it is full of the liquid mercury, and what happens when it gets warmer is the movement of all of the particles that has increased has the effect of having them collide with each other in the walls of the container so that they push against each other slightly, and what we experience is something known as thermal expansion. The mercury actually physically expands and it rises up the scale. Now that is temperature. It is the observation of how, on a large scale, all of the particles are vibrating. The more temperature, the more vibration the individual particles have. A little bit for later on, it's actually measuring the kinetic energy of the particles. But for now, don't confuse it. It is a snapshot, an indicator of the amount of motion present in the vibration of the solid crystal, or in the swirly, squiggly motion of a fluid sample. Now, the next thing we want to talk about is thermal energy. Thermal energy is an energy store. Thermal energy is how much energy in joules a substance has at any particular point. It is a measurement of the kinetic energy and something also known as the electrostatic potential energy, which is to do with the bonds that are holding the atom together. We don't need to worry about that one just yet. But for now, imagine this, that the more kinetic energy that the little tiny particles have by vibrating around, the more thermal energy it has and the more temperature it has. The final word, heat, you will remember, is the energy transfer, when thermal energy moves from one place to another place, from a hot object to a cold object. A cup of tea in the room loses the thermal energy to the environment via heat. Heat flows sometimes, and is also measured in joules. We're now going to talk about the connection between thermal energy and the temperature. If I put in thermal energy, because this is an open system, then what I would find is my thermal energy would go up. The question is, what would the temperature do? The temperature would almost certainly go up, so long as there was no breaking of chemical bonds or melting of ice. If it was a straightforward sample of water that we were heating, the temperature would go up. But by how much? We need a formula that links these quantities together. And indeed, there is a formula that you need to know. We'll start out by writing the energy, in this case thermal. And for whatever reason, in AQA, they don't put a little symbol to represent the fact that this is thermal energy. You will just have to trust me when I put E on the board. In this context, I'm talking only about thermal energy. The energy is connected to a number of things. But what it's going to do is it's going to cause a temperature rise. Now, what symbol do we use for temperature? Temperature is an interesting one. If I was talking very specifically about a very specific temperature, say the melting point of ice, or the freezing point of water, then I would represent it with a big capital T and say that it was equal to 0 degrees Celsius. But this is a specific temperature. Imagine if I was talking about the difference between two temperatures. Imagine I had one temperature that was equal to 10 degrees Celsius, and I had another temperature that was equal to 5 degrees Celsius. Then the difference between them would be 5 degrees Celsius. But how do I represent, using symbols, the difference between one temperature and another temperature? And second, how do I indicate to my fellow physicists that I mean any 5-degree temperature change, not specifically the 5-degree temperature change between 10 and 5. I could be talking about the 5-degree temperature change between 25 and 20 degrees Celsius. So I need a new symbol to represent that. Scientists, they had a good old think about it, and they came up with this, that the symbol to represent the temperature change was as follows. So temperature change is given the symbol delta theta. Delta theta. Two Greek letters. Delta theta. It means the change in theta, the symbol they've given for a temperature difference. So delta theta is just equal to the difference in temperature. It's equal to, in this example, 5 degrees C. And so delta theta is going to appear in this equation. Now, I've not given myself enough room, so I'm going to start again slightly further down. E, the thermal energy we put in, is going to cause a delta theta. We're going to get a temperature rise at the end. Delta theta appears just there. But it's also going to be dependent on some other things. You see, if I put some energy in to a small bowl, say I was going camping and I had a little camping stove and I was heating up some water to make myself a cup of tea, I would find that that energy released by the burning, the combustion, would produce a thermal energy that would increase the temperature of the water. But now imagine this. I have got that same stove and I put it underneath a tin bathtub, filled it with water. Now I've got 100 times more water, and that little flame that was so good at boiling my cup of tea is now fairly rubbish at boiling a whole bathtub of water. You see, what's happening is that thermal energy is being shared out amongst all of the atoms that are present. Some atoms are taking a big chunk, some atoms are taking a small chunk, but on average they're all taking some. If there are more atoms because there is more mass, then what you will find is that each one of them will receive a slightly smaller slice of the thermal energy. So the more mass there is, the less thermal energy each of those atoms will get. And as a result, the temperature rise will be less. So into this equation, I've got to include the mass. Mass is competing with the temperature rise. And so mass is going to sit here as well. For a given amount of thermal energy, the more mass, the less temperature rise. And for a given amount of thermal energy, less mass means more temperature rise. Something that is small is easier to heat than something that is large. Why does the Christmas turkey need to go in the oven for so long? It is because it is very large and it takes a significantly larger amount of thermal energy to bring it up all to the right temperature. There is one more thing that affects the temperature rise that we see from a given thermal energy input. And that is specific to the material that we are heating. Some materials, they heat up really easily. I'm being not very careful with my language there. What I should say is for a given amount of thermal energy, some materials will rise in temperature by a large amount. Other materials, for the same amount of thermal energy, won't rise up in temperature the same amount. They will rise up much less. And so how do we put into this equation something that is dependent upon the material? If we are, say, heating up lead or iron or glass or water, what do we use? Well, we use something known as the specific heat capacity. The specific heat capacity sits there, symbol C. C is the specific heat capacity. And I want you to think about it like mass. Remember, when there was more mass, the energy went in and it didn't affect a very large temperature rise. The specific heat capacity, when it is very large, that thermal energy will go in and it won't create a very large temperature rise. It works exactly the same as mass, but not now having anything to do with how many particles there are. It is more to do with what those particles are doing with the energy. A larger specific heat capacity means that the temperature rise will not be so great for a given amount of input thermal energy. So a very good question is, why not? Why does one substance have a different specific heat capacity to another substance? And a very good example of that is water. Now, water has a very high specific heat capacity, higher than nearly any other known substance. The question is why? And it all comes down to what water is like on a microscopic scale. You see, if I had a gas of, say, argon in this room, of which 1% of our atmosphere is made of argon, I would find that each of the particles was a single atom of argon. And that any input of thermal energy would just result, and could only result, in them moving more. And so it uses all of the thermal energy that has gone in to turn into a temperature rise. But what about water? Water, as you know, has the chemical symbol of H2O, two hydrogens connected to an oxygen in a molecule. Now, one of the things that can happen when you input thermal energy into water is that it can make the distance between the hydrogen and the oxygen increase slightly or decrease. In fact, the whole molecule can stretch and distort. The distance between them could increase, the angle between them could increase. It can do other things with the thermal energy as well as just move faster. And in fact, because it is asymmetric, it is not a symmetrical little round ball like the argon atoms, it is also capable, and this is the thing it loves to do, is spin round really fast on the spot. And it will take some of the thermal energy and just spin around really fast on the spot, but not, of course, lead to any rise in temperature. So here we have it. The thermal energy goes in and it causes a temperature rise. That is offset by factors trying to limit that temperature rise, which is how much mass we have and the specific heat capacity. Let's talk about units. The units of thermal energy are joules, the units of mass are kilograms, and the units of specific heat capacity are joules per kilogram per degree C. The unit of temperature change is degrees C. There is a required practical that looks at recording data of specific heat capacity of an object, and we'll have a look at that next.